Okay, I think we're about ready to go ahead and get started for the afternoon sessions. So I would ask you all to come on in, get your cup of coffee or your beverage of choice and have a seat. So this afternoon, we've got some climate change and extreme weather events going on here in this room. So button down and batten the hatches. Okay, our first session, session 5, is going to be impacts of climate change. And it's going to be chaired by Laurent Dubus, who is a senior scientist on weather and climate at RTE in France, the French transmission system operator. We're very glad that Laurent was able to join us from France this afternoon. He's going to be chairing virtually, and I'll let him go ahead and begin the session and introduce his panelists. So Laurent, let me turn it over to you.
Thank you, Charlie. Good afternoon, ladies and gentlemen. It's my pleasure to be here today, or to be here virtually at least. Apologies for not being with you in person, but I had strong commitment in Paris. And so thank you, Charlie, and the organizers for making it possible to attend remotely. So indeed, we will have a session on impacts of climate change with 3 very good speakers. I must say that I'm very happy to see that climate change issues are now a regular topic at the agenda of this workshop. Since I think the first time was 3 years ago when we organized it with WMC and Alberto Ciocoli. And since then it has been there all the time. And I think it's extremely relevant considering the targets we need to fulfill towards the net zero power systems in particular. So today we will have 3 speakers. We will have 3 presentations of around 20 minutes each, and then we will have a panel discussion and question and answers with the room. So our first speaker is Sara Pryor. Sara is a professor in the Department of Earth and Atmospheric Sciences at Cornell University. And Sara, the floor is yours, please.
Hello everybody, and I too am currently in Denmark, well in Europe. I'm in Denmark visiting the Department of Wind Energy here at the Danish Technical University. So hello from Europe. So perhaps it's not necessary for me to remind you, but over the last 20 years or so, we've seen tremendous growth in wind energy installations around the world. And if we look over the last 20 years, we've seen annualized increments of about 14% year on year. So this is really the rise of this important renewable energy sector. So now we have about 6.5% of global electricity supply from wind. And here in the US, we receive about 8.4% of supply from wind. If we look at the figure on the left here, it reminds us that in the US, we've tended to focus on onshore deployments, but the figure on the right is, of course, representative of the next generation of wind energy deployments. Here we have 16 lease areas along the US East Coast that are sites of active development, and 6 additional lease areas were auctioned successfully by BOEM in February of this year. So once these are fully operational, they should supply of the order of 4% of our national electricity supply. So clearly the wind energy industry is already playing a key role in decarbonisation of our electricity supply. And in this piece of analysis, we asked the question, okay, what if we were to continue with the expansion of the industry at current rates, or we were even to accelerate them? So the graph on the left here shows for the 4 IPCC socioeconomic pathways. So the different colors are the different pathways. If we follow them as specified by the IPCC, it's the solid lines in terms of cumulative CO2 emissions and the global temperature response on the right-hand axis. If we were to take what is referred to as the most likely, although possibly optimistic scenario, the 4.5 scenario, if we were to follow a technically feasible deployment scenario, we could in fact, under that otherwise self-consistent socioeconomic pathway, perhaps limit global temperature increase to 2%. So it's clear wind can play a really key role here. That having been said, of course, wind energy is part of the solution to avoiding climate change, but is itself responsive to global climate non-stationarity. So about 2 years ago, we did a synthetic review of studies that had sought to project the possible changes in power density. So that the power density, so the amount of energy in the wind, goes with the cube of wind speed. So we did a synthetic analysis of all of the studies that had sought to project how much will the energy density in the wind change by the end of the current century under different emission scenarios. And we found 11 credible studies in North America, all of which suggested the wind energy density would remain within about 10% of historical norms. There was a tendency for studies to show slight increases in the southern Great Plains and declines in the West. A similar number of credible studies for Europe, most of which showed increased resources in the northern parts of Europe, the Baltic Sea area, and declines in southern Europe. But for most of the globe, there was a real dearth of analyses. And even the studies that have been done in North America were limited because they tended to focus on either the mean wind speed, which is not very strongly related to power generation, or the energy density, which is itself also not a perfect proxy for power generation. So if we think about how can we make better projections of wind power generation, if we step back, we can say there are 4 real tools that we as climate scientists can use. The first is global Earth system models, where we take the 3-dimensional atmosphere, the ocean, the cryosphere, and we break it down into grid cells. And then we solve a numerical system of equation at the center of each of those grid cells. But the main challenge here is that those grid cells are typically 100 kilometers by 100 kilometers in the horizontal dimensions, and a couple of 100 meters or deeper in the vertical direction. So they really don't capture the wind resource. So we're going to set that one to one side and say the other 3 are plausible for use within the wind energy industry. First is to use global models with regional refinement. So we have much smaller nested grids over the region of interest, or we can apply regional models over a limited area of the globe and then use our global models to describe what's happening outside our domain and advect in our large-scale synoptic circulation systems. Or, of course, we can use statistics to link atmospheric phenomena to the local variable of interest. So I'm going to present today an analysis using those last 2 approaches. And maybe I should say that whereas it is patently obvious that increasing greenhouse gases will increase global temperature, it's very hard to a priori postulate what the impact should be on wind resources at a given location. So we can't sort of set up a theorem and then falsify that. We really need to do the primary research. So our study, I think, is unique, at least it's highly innovative in that we were able to obtain daily expected power from wind farms operating across North America. So daily expected power was provided by the wind farm owner operator. And what it represents is how many megawatts per day would be generated from that wind farm if there were no operations and maintenance, no curtailment for grid integration, and no electrical losses. So it's a representation of essentially if the wind farm could operate with only geophysical constraints. So those data were given to us on the agreement of that we would protect data privacy. So I'm only going to refer to the sites in terms of the geographic region they're located in. So we had 7 sites within the Southern Great Plains where we had daily expected power. The other part of the agreement is that we never present expected power, but we actually present capacity factors. So these are just saying for each day, we count up the number of megawatt hours and we divide by the total possible if the wind farm were operating with all wind turbines generating their nameplate power. So the figure on the left shows the location of the sites from which we have data. We have between 2 and 7 years of daily expected power. The figure on the right is to try and emphasize why we don't believe that talking about changes in annual mean wind speed is at all productive. What's shown on the bottom panel here is for the sites just in the eastern portion of the US, the annual mean wind speed across all of these sites. So you can see for all of them, it lies between about 6.5 meters per second and about 9 meters per second. So a very narrow range. But on the bottom here, we have the probability density functions of those daily capacity factors and the mean capacity factor on the x-axis here. So you can see that the capacity factors at these sites operated between about 29 and 47%. So there's a massive span in the quality of the power, if you like, being produced by these sites. And it's because, of course, if we think about the link between wind speed at hub height and the amount of electrical power produced, it's 0 below the cut-in wind speed that's typically between 3 and 4 meters per second, rises rapidly as wind speeds increase, and then power plateaus once we've reached rated power. So you can see there's enormous variability in power that would never be manifest as in knowing only the annual mean wind speed. So we've taken these daily expected power, and we've done 2 pieces of independent analysis trying to project forward in terms of wind power generation at these sites. In the first analysis, the piece that I took the lead on, we applied the weather research and forecasting model for the domain shown within this large black box. And outside, all of our lateral boundary conditions were supplied by the Max Planck low resolution Earth system model. So essentially, we're nesting our high resolution WRF model at 12 kilometers within that global model. We ran our simulations from 2009 to 2049 under the high emission forcing. In the parallel piece of analysis, my postdoc, Jacob Coburn, took a statistical downscaling approach. So we take the expected daily power at each site and develop transfer functions that link atmospheric conditions, so specifically the circulation pattern and the pressure gradients to that daily expected power. Once we've got that transfer function that links the meteorology to the power, we can apply that transfer function to any model output. So in this case, we used 4 different global models and 4 different emission scenarios and projected daily power out to the end of the 21st century. So the idea being these are completely independent analyses where they agree in terms of a projected sign of change. Perhaps that gives us some confidence. So I'm going to focus on the dynamical downscaling, and of course, the first question we had to ask is, if we run our WRF simulation and for each hour we take the wind speed that we simulate at the hub height of that operating wind farm, and we apply the power curve linking wind speed to power production for that specific wind farm, so it's strongly linked to the true wind turbine that's operating, how well do we capture the mean capacity factor from that we're also getting from the expected power? So this scatter plot shows for each of these sites, when we compute the annual mean capacity factor from our WRF simulations and we look at the observed expected power, how much do we, what degree of agreement do we have? And what this shows is that we do capture the macro scale variability. So specifically, our simulations do correctly represent the better wind sites and the less good wind sites. But of course, the agreement isn't perfect, and that's because at 12 kilometers, we still don't resolve all of the phenomena that cause variability in wind resources. But nevertheless, the agreement, we decided the agreement was good enough that we could use this simulation to make projections of the future. So the first thing we did was take our WRF simulation and compute for every year starting in 2009 out to 2049, what's the annual capacity factor at each of our operating wind farms. So we can see we've got 2 here in the Northern Great Plains, 7 in the Southern Great Plains, so the different hues represent the different sites, 3 in the Midwest and 7 in the Northeast. So if we apply trend analysis to these time series, we find that essentially only the sites in the Northern Great Plains show a significant tendency. It is a decline. And if we look at the median, so the average capacity factor in each decade, we can see that there is for the Northern Great Plains, there is a tendency towards declining capacity factors, or perhaps we should more correctly say the 2030s and the 2040s exhibited lower capacity factors than the 2010s and 2020s. Of course, that's not symptomatic necessarily of a secular trend. It could be internal climate variability. But nevertheless, either way, we can say only those 2 sites exhibited any lowering or equally positive change in capacity factors. What we're seeing is things like ENSO and the PDO, the PNA, so these internal climate modes continue to dominate. So there's variability rather than a trend. The other thing that I know is really important in terms of thinking about integration into the grid is thinking about production droughts, so periods with extended periods with anomalously low power. So we also used our WRF simulations to look at that, and I'm just going to show 2 exemplars here, one from the northeastern US and one from the Southern Great Plains. So first we can say this is the cumulative density function of the daily capacity factors at these 2 sites, with black being modeled from WRF and the colored lines being our observations. So we're broadly capturing daily capacity factors. If we take a 30-day running mean, so now really we're trying to smooth out the seasonal cycle, so we show when in a given part of the year we show higher or lower production, we get the figures on the left here. So this model chain of WRF using input from the Max Planck Institute does a reasonable job of the seasonal cycle, but you can see that the Max Planck Institute essentially has too strong a synoptic regime during the spring. So it's funneling in too many cyclones into WRF, and WRF propagates them in towards the northeast. So we have an excess power production here, or capacity factor here in the spring. In the southern Great Plains, we see across virtually all of the sites here that the model doesn't quite return to higher capacity factors early enough in the year. So essentially this full recovery is delayed. So we clearly, this tells us that we need to invest further in improving our models to capture the synoptic regime better. These figures also remind us that if we want to talk about anomalous power production, we need to do it with this seasonal cycle in mind. So what I show on the right there is taking each 30-day period and saying, relative to the mean seasonal cycle, is this an anomalously low summer period, rather than setting a single threshold across the entire year? So essentially we're saying anomalies are defined relative to that seasonal cycle. We can think about that in terms of drought probability. So we've set our threshold at 20%. So it's the lowest 20% summertime days, or the lowest 20% wintertime days. If we look at that, those projections, again, we see no change except for those northern Great Plains sites where we see an increased probability of drought by the middle of the century and a decreased probability of bonus periods, so higher than average production periods. Otherwise, we see a continued signal of variability and not secular change. Realize this is a very busy figure, but in it, what I've tried to do is integrate the dynamical downscaling that I did, and also Jacob's statistical downscaling. So if we focus on the northern Great Plains here, so remembering we had 2 sites here where we have observational data. When I look at the output from our WRF simulations, we see an average lowering in the last decade of almost 2 percentage points in capacity factors in the middle of the 21st century. If we look at statistical downscaling of every realization from the 4 Earth system models across the 4 emission scenarios, we see that they span 0 for 2 of the Earth system models and indicate small magnitude declines, about 1 percentage point from the other 2. Essentially, we see a similar signal in all of our regions, that out to the middle of the 21st century, we really don't see a consistent sign of change. If we look further out towards the end of the 21st century, we start to see a dominance of the red colors here, which is a signal of declining capacity factors. So to some degree, this is not entirely cheerful news. We can say we anticipate perhaps declines of between 1 and 2 percentage points in capacity factors. But I think it's important to contextualize that in terms of the changes in capacity factors we've actually seen from technological improvements. So if we look at wind farms that were commissioned between 2014 and 2019, they were around 41% in terms of a mean annual capacity factor, whereas the previous generation had capacity factors of only 29%. So at least some of these projected climate changes, or indeed possibly all of them, can be overcome if we continue to improve the overall quality of our wind turbines. So there's no need to panic, but I would strongly advocate that, given we're thinking of investing, $500 billion in developing the offshore wind resource along the US East Coast, there ought to be at least some investment in understanding the stability of the wind resource in which they would operate. Thanks for your time, and I believe my time is up.
Yeah, thank you very much, Sara. That was extremely interesting, and I guess many people in the room will be waiting for your papers to be published I will be one of those at least. Thank you again, and welcome to question at the end of the presentations. So let's move to our second speaker who is on site. Dr. Haupt is a senior scientist at the National Center for Atmospheric Research. She's also the deputy director of its research application laboratory and contributing director of the World Energy and Meteorology Council, where we have worked together for more than 10 years now. Our renewable energy work spans wind and solar power forecasting, but also coupling mesoscale to microscale models and estimates of climate impacts. And Sue, the floor is yours, please.
Thank you, Laurent, for a great introduction. And I'm going to emphasize the interannual variability and its importance to really understanding how to operate future systems. Now, as an introduction to that, I have a few maps here on current climate, and I want to point out the huge impact of interannual differences. Now, we often have patterns, teleconnection patterns in the atmosphere that cause predominant conditions over prolonged periods of time. One of those, and probably the most famous example, is ENSO, El Nino Southern Oscillation. Now, on this plot, the left version of the plot, oh, wait a moment, I missed the wrong one. Yes, okay, here's my motivation one. And it's actually work that is relatively old now, but it was done on NCAR's Climate Four-Dimensional Data Assimilation Database, looking at the difference between an El Nino year, in this case 1998, versus a La Nina year, 1999. And you can see the big differences when you subtract one pattern from the other. This is mean winds in January at 06 UTC. We find that there can be very large regional differences. For instance, if you lived in Northern California, in the El Nino year, you had 6 meters per second more wind. Now, if you put that through the nonlinear portion of the power curve, that would be quite a bit of difference in wind. However, if you lived in Southern California, you could be negative 6 meters per second. So these regional differences can be quite profound. The plot on the right is the variance of that. And again, you're looking at rather high numbers on the order of -60 in this case. And when you think of that, that's equivalent to a standard deviation on the order of 8 meters per second. Quite large differences, huge impacts for wind energy. So I'm going to talk about a few different studies, all of which were done in collaboration with the National Renewable Energy Lab and with NCAR, where I am based. And the first study used that four-dimensional data assimilation database. It's a 20-year climate reanalysis. And we were working with NREL, looking at differences it would make in their READS model for determining what deployment to use. They wanted to look at interannual variability of the wind and solar resource. So we started with this current climate database and started by looking at mean 80-meter wind. No surprise, the huge resource we have in the central part of the US, but then also calculating interannual standard deviations. And not surprisingly, the largest deviations tend to be in the same areas where we have the largest resource and the largest wind deployment, which implies that, yes, we are going to have variability in current climate wind resource. Also, solar resource, the typical see southern US has a much bigger resource, especially in the Southwest, and the standard deviation interannual does have a pattern that kind of matches that of the mean pattern. Now, for the Reed's model, to do their deployments, they like to slice and dice these databases in lots of different ways, using 356 regions over the United States and looking at differences between time of day, defining morning, afternoon, evening, night, 4 periods, and 4 seasons, summer, fall, winter, spring, so that we can take all the data, slice and dice it in any way we want to look at the variabilities. So we took those maps, those mean maps of hub height, wind speed, solar radiation from this current climate. We broke that up into patterns using self-organizing maps. That's a machine learning neural net-based method where we can find predominant maps of variability. They do look like things that we would expect to see over the US. So we were convinced that 24 maps were about right for this particular study. Then we looked at the current climate simulations of climate models, three combinations of climate models and regional climate models, which Sara just explained. And we looked at the projection of the SOMs onto these certain maps, and we chose 3 different combinations that we chose to use for our future projections that we think matched the database from the current climate best. Okay, now because, of course, we're talking about climate change, we applied SOM-specific adjustment factors for each season. So maps like this to account for warming temperatures and the expected changes in the wind patterns due to this SOM analysis that we did. Okay, cut to the chase. What is the likely change in the wind and solar output over the United States? So what we're doing here is we're looking at the difference between a 20-year climatology centered at 1995 from that a 20-year climatology centered in 2060. And again, we can slice these in terms of season and time of day. So for the morning, wind changes, we see that typically for all seasons, well, not all seasons, sorry, across the Southwest and really most of the southern part, a decrease in wind. Spring, especially across the West, decrease everywhere except Texas. Summer, we get increases in the southern areas, decreases northern areas, and a transitioning period in the fall. Okay, solar radiance, we see increases across the South in the winter, spring, decreases across the middle part, increases across California, bits of New England. Summer, we see predominantly increases. Fall, a little bit less change. But when you look at the scales, you see that it's between about -10 and 10%. So what we learned from this study, using this method, we're not going to go through all the details, using these 3 different, climate scenarios for high emission scenarios, we could calculate changes in the wind and solar, and we could slice and dice the variability according to season. We found that the predictability, the predicted change is usually within about plus or minus 10%, although we found a few places and times where it hit about 20%. Regional changes are again within about plus or minus 10%. We did see variability seasonally, less variability diurnally. Okay, another study that we did with NREL really looked at the changes in the patterns. I think Bri is going to talk about some figures. We looked at different representative concentration pathways and different emission scenarios. It depends on whether some of the older CMIP runs versus younger CMIP runs. But we did look at low, medium, and high emission scenarios. And what we did in this case was we looked at the impact on energy sector. This power system component, when we see here on the left part of the table, it's going to look at agreement among studies, the quality of the evidence, and the confidence in our evaluation. So it really is synthesizing multiple studies that have been done to this date. This was work led by Michael Craig, currently a professor at University of Michigan, working at NREL at the time as an intern. Found that electricity demand, yes, we have high confidence in that result, and finding the increased total annual demand, which implies on the right side, increased generation. For thermal generation, we're finding also high agreement, high confidence, robust evidence in increased summertime curtailments, largely due to the thermal discharge regulations, which implies that we're going to have a reduced capacity value of those units. Transmission impact as well, of course, reduced capacity during peak demand, which means we need increased transmission investment. Then we're getting to the renewables, hydropower, wind, solar, and the results for this are either medium or low confidence and agreement between studies. And what we're finding in general is regional differences, much as we saw in that first analysis we did, that there are regional differences, there are seasonal differences. We need to understand that variability to really make sense of it and make smart decisions for where to deploy things in the future. Now, finally, I'd like to end with a final study that was done collaboratively between NREL and NCAR. And this was a case study over a very small region. Now, most of the studies use climate models that have resolutions order of 100 kilometers and regional downscales on the order of 12 kilometers. This particular one used downscaling to 4 kilometers, and that's what we meteorologists like to call convective resolving. That means we think we can get the clouds right in the model and we don't have to parameterize them. And by getting clouds right, we get a lot of the dynamics right, and it gives us a lot more confidence that we're getting correct results at the very specific regions. And this is why NOAA runs their HERC at 3 kilometers to get that convective resolving. Now, what we find is, over Texas, and I'm going to be showing a few of these maps where we show the baseline capacity factor, in this case for solar, over different regions in Texas. Then we show 5 different little Texases, in this case, the purple ones, that show each of the 5 different climate models that were downscaled. And then to see whether there was sufficient agreement that we believe our results, this bottom little map in green, the green shows the regions where 4 or more of the models agreed. So we have very high results. Now, for solar, what we see in changes in capacity factor, they range from on the order of minus 0.6 to 2.5% on an annual average. And, again, it's regional as to where we see changes, increases in capacity factors in southern and western Texas, decreases in panhandle regions. Now, if you look at the bottom left, we can see the seasonal variations. Baseline are the solid curves, dots are the 5 different scenarios average over each month. We see decrease in capacity factors in winter and late summer on the seasonal curve. The diurnal curve, we see an increase in capacity factor in the late morning, which is an interesting result useful for Texas. Similarly, for wind, we see in general average increases order 1.3 to 3.5%, small percentages, but could be significant given potential variability, especially see increases in West and East Texas. Across all of these, large agreement between the models, decreases in the Panhandle and Southern Texas. Seasonal changes are relatively small, and we see an increase in capacity factor over most of the day from the baseline. Now, this morning we heard about ramping and having the dynamic margins, et cetera. So to get at that issue, are we getting more variability? This study looked at the 95th percentile of hourly variability, calling it, an analysis of the extremes and changes, basically a ramping type metric. On the left is the solar variability. We find that on average, it's on the order of 42 to 57%. Not as much change in capacity factor there as one would expect. Wind, the reference is on the order of 17 to 49%, but we do find some changes with positive numbers in more northern Texas, negative numbers more in southern Texas, less agreement across the multiple models. So in summary, just pointing out that climate projection should include information on the variability on multiple temporal and spatial scales if we're going to be able to use these well for planning. As we're moving forward, we're getting to the place where we can do these long-term simulations using cloud resolving scales, 4 kilometers or less. In fact, at NCAR, we've recently completed what we call the CONUS 404. That's the contiguous United States, 4-kilometer resolution for 40 years, working collaboratively with USGS on their Cray computers. The plan is to do something similar for future climate. It hasn't been done yet. And I want to finish with the point that ideally one should have a consistent database, correlated wind, irradiance, temperature, humidity of both current and future climate for coordinated planning. And in fact, Justin Sharp has a new initiative here within SIG trying to look at how to develop such databases and how to use them for coordinated planning. So with that, I'll stop and can move on to the next speaker.
Well, thank you very much, Sue, for this great talk. Extremely interesting, and also converging with some analysis we did in Europe. So that's very good. We'll indeed move to our last speaker today with Dr. Bri-Mathias Hodge. Bri is an associate professor at the Department of Electrical, Computer and Energy Engineering, and an associate director and fellow of the Renewable and Sustainable Energy Institute at the University of Colorado. Bri, the floor is yours, please.
Thanks so much, Laurent. And, thanks so much to Sue, Ellen, and Sara for the sort of introduction. They've given great examples of how the changing climate is changing the wind and solar resource. And I'd like to talk a little bit about the implications of that and the other changes that all those meteorological variables are undergoing on power system planning and operations. And so I just want to start off with this. I'm sure folks don't need any more proof that global warming is happening, climate change is happening. However, I really feel like this brings it into striking relief in that we can see the mean global monthly temperatures from 1851 and how those are changing, the last decade, 2 decades really, doesn't look so great. So I want to make 2 points with this. One is that we are planning for 50-year horizons or so in the power system. And so we need to desperately take into account any additional changes that we might see here into that planning process. And the second is just that some of these changes are already included in our data, which we may not recognize. Okay, so we talked about a couple of the different changes that the climate change is having on power systems. So things like the change in the solar resource, the wind resource, a little bit about the hydro resource as well, but it has other impacts as well. So load is obviously a big one. In the US, we like to think of load, peak load, especially being driven by air conditioning demand. So it's a summer problem in most of the country. And so, higher temperatures, more air conditioning, higher loads, and that's part of it. But what we also see, and I want to talk about this a lot more later, is a winter peak as well. And this is both sort of because of climate change and more extreme weather events during that time period, but also because of responses that we're taking to climate change. As we electrify more things, we're going to be changing our load patterns as well. And so I want to show later an example of a system that actually is basically experiencing a dual peaking system and some of the challenges that go along with that. So load obviously is a big impact. Thermal plants can also be impacted in that, a lot of the times during the summer, especially, they aren't able to cool fast enough with hot water temperatures. And so you can have summer D rates on those. And so when you add all these up, you have a little bit less, capacity available from thermal plants. You have a little bit less from hydro plants. Perhaps your wind is reduced during that time. Perhaps your solar is reduced, and you increase the demand during those times. If we're not taking those into account, that really gives us a pretty large gap in our planning reserve margin when we're doing these power system planning studies. If we look at that as well, just from the sort of operational perspective, looking at an economic dispatch stack, we can see each of those individually and then how they cumulatively could potentially cause issues. So, this is just our base case, the no impacts case, pretty normal sort of summer day in the US for load, peaks in the sort of early evening period. And this is perhaps how you would fulfill that load in a system. With the thermal plants, now, we have these D rates. And so basically we just lop off a little bit of this pink and that drops down. And so, that will leave a little bit of a gap here during the peak period. Hydropower may also be a little lower, so may not be able to shift that around as much, may run into must-run constraints on the hydropower. Wind could perhaps have similar impacts. So, the wind resource could be reduced a little bit. Solar not being able to produce as much just before that peak might also impact things. And then, of course, increased demand just exacerbates that issue. So when you add these all together, we could see then from an operational perspective, again, how we may run into that sort of issue of not having sufficient generation capacity when we need to have it. So this is something I want to be clear about is not work that I was involved in, but for some collaborators at Carnegie Mellon. But this really shows that sort of dual peaking system, right? Because what they did in this study was they looked at TVA, the Tennessee Valley Authority. And so, sort of that middle America climate, right? Where you have hot summers and, the temperature can drop a little bit in the winter as well. And this just sort of shows the historical amount of load with different temperatures. So you have that sort of summer peak, but then you also get that winter electrification peak as well. And they showed here using a load duration curve how that can change in the different sort of timeframes under different climate change models. And the key thing I just want to emphasize here is, this may not be changes over all of your time periods, but they're the ones you're really challenged at, right? So your highest demand hours now become even higher demand. And so require, more planning capacity and then more operational sort of readiness to be able to handle that in a lot of cases. The reason why I think that is so great is I want to talk about a different system that has that same sort of issue. So, and that is the Duke Energy Carolina system. So recently at NREL, we conducted a carbon-free resource integration study with Duke Energy. And I want to talk a little bit about that. Now, I want to explicitly state here that this did not explicitly use climate change information, but really what I'd like to focus on here is that interannual variability that Sue Ellen mentioned before, and how that we can see that and the increasing of extremes on an interannual basis, how that can impact the planning and then operations process. Because when we are doing this planning, oftentimes we're doing it based on a single, say, year assumption. We're trying to utilize that consistent meteorological data set, which is great. But looking only at 1 year can really change the picture if we have some extreme events, even during just 1 or 2 weeks during the rest of the system. So the Duke Energy system is very unique in that it has a very high share of power from nuclear power, actually. So roughly 50% on an annual basis. And so this leads to very interesting sort of decisions that are being made moving forward. So North Carolina has goals to reduce its carbon emissions by about 70% by 2030, and then to zero essentially in the electricity sector by 2050. And so if we look at different cases, so the base case here is just the pure economics case without those policies. The policy case tries to meet those targets. And then we have a final one that is a little bit tougher, a policy with absolutely no fossil fuel. Because even when you're doing a planning model, because you're not looking at the 8760, you might keep a little bit of, say, gas CCs or CTs. You don't think you're going to use them, but you're holding them just to, meet that planning reserve margin, having something available. And in this no fossil case, we really have to replace them by something else. In this particular case, we looked at what we're calling renewable CTs, so combustion turbines that are run by some sort of renewable fuel, whether that's a hydrogen or a biofuel or a renewable produced natural gas. But this becomes a critical resource toward going to that net zero and also fulfilling that sort of dual peaking interannual variability issue. So in this case, you have this very large build out over that time, mostly here driven by new solar installations and then storage. Here, particularly, we just looked at what I would call diurnal sort of storage, so 2 through 8 hours. And so things like long duration storage might be able to fill some of that gap by the renewable CTs. So with that system, just one thing I'd like to quickly point out is reaching those 2030 goals compared to the base case of 70% reduction in carbon is, from an economic perspective, relatively easy. So about $7 per ton of carbon for the cumulative CO2 abatement cost during that time, with a range that's a little bit bigger, from about 6 to 20. That 2050 next step, though, is the difficult part. That has a much higher cost, about $27 a ton by 2050, and really that's even just it's that last little bit that is the most difficult and most expensive here. And so I want to look at this take this from the purely capacity expansion and look into the operational aspects, because it's a lot different looking at every hour of the year than it is just looking at time slices, no matter how many of them you do. And so I'd like to look out and compare a 2024 build, which is sort of our baseline. And this is all based on 2012 weather. A 2030 build, show how that looks, and then a 2036 build. But I want to put 2018 weather on that 2012 to show the difference in interannual variability and highlight the implications of that dual peaking system in a year where they had sort of an extreme winter for them. Okay, so this is what those dispatch stacks look like. This is your sort of current case, if you will. Your nuclear power producing, about 10 gigawatts normal. You have some coal in the system and a decent amount of solar already. As you go toward 2030, increasing solar, a little bit of increasing storage to sort of meet those nighttime peaks. You retire coal in this particular case, that gets mostly replaced by gas, CCs or CTs. And then if you look to the 2018 case in the summer peak dispatch, it's not that different. The system isn't having trouble meeting that. It's actually the winter peak that becomes the issue in this case, because dual peaking nature, and the fact that you're, via cold temperatures, your peak happens not at 7 p.m., but rather at 7 a.m. And, your wind is starting to fall off, generally speaking, during that time, and your solar is just starting out. And so in that winter peak dispatch, the current case, they might be utilizing a bit of coal. In the 2030 case, might still have some of that coal online, but utilizing it less. In the 20 retire coal scenario, that has now been replaced again by that CT. And here we see that winter peaking period, that 7 a.m. before your solar comes on, you're really tapping out your planning reserves of CCs, CTs. The good news is you can do it. You do have to do a bit more imports perhaps than you're used to, and hope that cold front isn't covering, say, the entire East Coast of the United States. But, this is one of those challenges that we're going to be facing, getting from, large reductions like 70% all the way to 100%. And one thing that I think is really critical here, so I just want to emphasize, again, this is looking at that case, and when you use those renewable CTs, these would be the equivalent of your peaker units today. How much capacity do you need, and then how much energy do you get from them? Just like peaker units today, they have a low annual capacity, but when you need them, you need most of them. And so, this just sort of shows the energy, in this case, in MMBTUs that you might utilize from those. You see some of those peaks in the winter because of that dual nature that we talked about, some during the more traditional peaking summer season. And then again, sort of a late fall, early winter, you have to dip into those again. And so, again, this could be seasonal storage, this could be hydrogen turbines, this could be a biofuel alternative. But to me, this is really one of the critical issues that we need to be able to solve in order to handle the impacts of climate change on power systems and move toward a net zero electricity system. So with that, I'd like to thank all the great folks at NREL and NCAR and other places who have worked on this. Some of whom are unfortunately no longer at NREL. And I'd be happy to answer any questions. Thank you.
Thank you, Bri.